All right, let's dive into some physics today. We're going deep, deep into how things move. But not just like straight lines, like, boring stuff.
Right.
We're talking 2 dimensions.
Yeah.
Curves, arcs, the whole thing. You'll be surprised, I think, how much this stuff can explain.
Yeah.
Like how a cricket ball flies through the air.
Yeah.
Or even why cars on a racetrack, like, bank on those turns.
It all begins with scalars and vectors, really. Understanding those.
Scalars and vectors. Oh, okay. Those words always kind of made my head spin a little back in school.
Yeah.
Remember, vectors had something to do with arrows.
That's a good way to think about it. So a scalar, it's like a simple measurement, right? Like, let's say it's 25 degrees outside.
Okay.
That's temperature. That's a scalar. It's only got, like, magnitude or size, you know?
All right, so a scalar just tells you how much of something there is. So what makes a vector different?
A vector has that how much, but it also includes direction.
Yeah.
So, like, instead of saying, I walked 5 kilometers,
Right.
you'd say I walked 5 kilometers north.
Got it.
That north is really important. It gives you, like, the full picture of the motion.
If it's like a scalar with a built-in compass.
Exactly.
Okay. But why does that even matter so much for understanding how things move?
Because knowing where something's going is just as important as how fast it's going.
Okay.
So let's say you walk 4 meters east
Okay.
and then 3 meters north. If you only look at the scalar part, the distance, you'd say, okay, I walked 7 meters total.
Right. But you wouldn't end up 7 meters from where you started.
Exactly. You'd be like somewhere northeast.
Yeah.
And that's where displacement comes in, which is a vector.
Okay.
And it measures that straight line change from start to finish,
Got it.
taking into account both distance and direction. In that case, it'd be 5 meters
Okay.
in a northeast direction.
And how do you measure that?
Well, we can use the Pythagorean theorem.
Pythagoras?
Yeah.
Like the A plus B C AT?
Exactly. So picture those walks like east and north as the 2 shorter sides of a right triangle, right?
Okay.
The hypotenuse, that long side,
Mm-hmm.
that's your displacement.
Got it.
That straight line. So 4 NROM plus 3 Dumetry gives you 5 NE1.
So even simple geometry helps us understand motion.
It all connects.
I never thought about it that way.
And this is just the start. Velocity, acceleration, force.
Yeah.
These are all vector quantities.
Okay. So vectors are important. I'm starting to see that. But how do we actually work with them? Like, is it as simple as just adding or subtracting regular numbers?
It's a little bit different. Let's start with multiplying a vector by a scalar.
Okay.
So imagine you have a car, right? It's going east at 50 kilometers per hour.
Okay.
That's its velocity. That's a
Yeah.
vector. Now you double the speed.
So it's going 100 kilometers an hour east.
Exactly.
Yeah.
Then you just multiplied that vector by 2. Think of it as like,
Okay.
stretching or shrinking an arrow, but keeping that direction the same.
Got it. Got it. But what about adding vectors? I feel like that might be a little trickier.
Yeah, for that, we use a visual method
Okay.
called head to tail. So imagine a boat's trying to go east,
Okay.
but there's a current pushing it north.
Okay.
We need to add those 2 vectors to find out where the boat actually ends up going.
So like we draw arrows for both of those.
Exactly. You draw the first arrow, then starting from the tip of that first arrow,
Okay.
you draw the second one. The line that connects the very beginning to the very end, that's your resultant vector. That's the boat's actual displacement.
So the boat ends up going like somewhere northeast then.
Exactly. Pushed off course by the current.
Yeah.
And subtracting vectors is just like adding a negative vector,
Oh,
flipping its direction.
got it.
Yeah.
So I'm getting the hang of this. We've learned the alphabet.
Yeah.
Now it's time to make some words. Right?
Right.
Okay. So let's apply this to some real motion.
Oh.
Let's picture a car taking a curve on a racetrack. How would we describe its motion?
All right. So it's going at a certain speed, but it's also changing direction constantly, right?
And that's what gives you like that feeling of being pulled to the side, even if the speed is steady.
Exactly. And that's a key insight. It's actually accelerating, even though its speed might be constant.
Okay.
To describe this, we need to introduce something called position vectors.
Position vectors.
Yeah.
What are those, like coordinates on a map?
Yeah, you got it. Imagine drawing an arrow
Okay.
from a fixed point, like the origin, to the car's location.
Okay.
That's the car's position vector. And as the car moves, that position vector changes.
Okay, so we're basically tracking the car's location along the path.
Exactly.
But how do we factor in, like, its speed and direction at any given moment?
That's where velocity comes in. Velocity isn't just speed, it's speed in a specific direction.
Okay.
It's the rate of change of that position vector.
Got it.
At any point on that curve, the velocity vector is tangent to the path.
So the velocity is always pointing in the direction the car's moving at that moment. This is
Exactly.
getting very visual.
Yes, it is.
And then there's acceleration.
Right.
We usually think of that as like speeding up or slowing down, but in 2 dimensions, it can happen even when the speed is constant.
Exactly.
Wait, hold on. How can something accelerate if the speed's not changing?
Because remember, acceleration is the rate of change of velocity.
Oh, right.
And velocity has both magnitude, that's the speed, and direction.
Right.
So if that direction is changing, even if the speed stays the same,
Okay.
the object is accelerating.
Oh, I see. So the car on the racetrack, even if it keeps a steady speed, it's still accelerating because the direction is constantly changing.
Exactly.
Wow, vectors are pretty cool. They really help you grasp this stuff.
They give us a new language to describe motion.
Yeah.
And we're just scratching the surface here. Imagine what happens when we delve into constant acceleration in 2 dimensions.
Okay, I definitely need a minute to process all of this.
Mm-hmm.
This is already way more interesting than I remember physics being in school. We'll be back in a bit to keep unraveling these mysteries of motion. Don't go anywhere.
Welcome back. I'm excited to keep going with this.
Yeah, me too.
Exploring the world of motion.
Fair.
We've got a pretty solid foundation with vectors now.
Yeah?
So let's see what happens when we introduce constant acceleration.
Constant acceleration.
But not just any constant acceleration in 2 dimensions.
Constant acceleration in 2 dimensions. That sounds pretty intense.
It is.
Can you remind me what exactly constant acceleration even means again?
Sure. It means that the object's velocity is changing at a steady rate.
Mm-hmm.
Think of a car, right? It's accelerating from 0 to 60 mph.
Yeah.
At a steady pace. That's constant acceleration in 1 dimension. But now imagine that happening in 2 dimensions.
Okay, so it's not just like speeding up or slowing down. It's also maybe changing direction at a steady rate.
Yeah, precisely. And the perfect example of this is projectile motion.
Okay.
Think of a ball being thrown across a field, right? It's got that constant downward acceleration because of gravity.
Yeah.
But its motion is this graceful curve. It doesn't just drop straight down.
Oh, right. Like that experiment where you drop one ball straight down and you throw another one like horizontally at the same time. And they both hit the ground at the same time, even though one travels like much further.
Exactly.
That always kind of blew my mind. I never understood that before.
That's a great illustration of how we can analyze 2-dimensional motion with constant acceleration.
Okay.
The key is we break it down into its horizontal and vertical components and treat those separately.
Wait, hold on. How can you separate the motion like that? It's all happening at the same time, right?
It is, but think of it as a mathematical trick to simplify things. You decompose the initial velocity into its horizontal and vertical parts. You can almost imagine shining a flashlight on the ball, right? At an angle.
Right.
And the shadow it casts, that's kind of the component of the vector in that direction.
Oh, okay. So you're projecting the motion onto 2 different screens almost.
Exactly.
One for horizontal, one for vertical.
Okay,
that's really helpful.
And here's where it gets really interesting. The horizontal component of velocity stays constant throughout the motion.
Really? Why is that?
Because we're assuming there are no other forces acting horizontally.
Okay.
Like in a simplified model. We're ignoring air resistance and things like that for now.
Okay, so it just keeps going at the same speed.
Yeah, horizontally. Exactly.
What about vertically?
Vertically, the object is under the influence of gravity.
Right.
Constantly.
Yeah.
So the vertical component is changing.
So vertically, it's basically in free fall.
Exactly.
Yeah.
Just like that experiment with the 2 balls.
Okay, this is starting to make sense.
And what's amazing is we can use the same equations we learned for 1-dimensional motion with constant acceleration, but we apply them separately to the X and Y directions.
Oh, wow. So those equations with displacement, velocity, acceleration as a function of time, all that, those seem so abstract in school, but now I see how it applies to real-world motion. It's decoding the secrets of the universe or something.
Let's take an example. Imagine a particle.
Okay.
Starting at the origin with a velocity of 5 meters per second, purely in the X direction, right?
Okay.
So it's not moving up or down. It's just moving horizontally. And it's accelerating at a constant rate of 3 meters per second squared in the x direction.
Okay.
And 2 meters per second squared in the e direction.
Okay.
Now, to figure out, let's say, its position and speed after 2 seconds, right?
Okay.
We can use those equations you were just talking about.
This sounds complex, but I'm ready.
Yeah.
So where do we even begin?
First, we need to recognize that initial velocity only has an x component, right? Meaning it's starting from rest vertically. After 2 seconds, its x velocity would become 11 meters per second.
Okay.
And its y velocity would be 4 meters per second using those equations.
Okay. So we know how fast it's going horizontally and vertically.
Yeah.
What about its position?
For that, we use the equation for displacement as a function of time. In the x direction, it's moved 22 meters.
Okay.
And in the a direction, it's moved 4 meters.
Okay.
So after 2 seconds, this particle is 22 meters to the right and 4 meters up from where it started.
Wow. So we can pinpoint its location after a certain time. It's like we have this power to predict where things will be.
That's the beauty of physics. And this approach works for all kinds of projectile motion, like a baseball flying through the air or a rocket launching into space.
Speaking of projectiles, I've always been fascinated by how, like when you throw something in the air, how it makes that like perfect arc, that parabola.
It's beautiful, isn't it?
Yeah, it's like so elegant and predictable.
Yeah.
Like it's following this like set path.
It is a beautiful phenomenon, and it's a direct result of that constant downward acceleration due to gravity, as we've been talking about.
So projectile motion is it basically any motion where the only force acting on the object is gravity?
Exactly.
Okay.
And just to make the math easier, we usually ignore things like air resistance.
Right.
At least at first.
So no wind, no friction, just gravity.
Exactly.
Okay, so that's our like idealized model.
Yeah.
For now.
You got it. Now remember how we talked about breaking down velocity into horizontal and vertical components?
Right.
That's key here too.
Okay.
Imagine you throw a ball at an angle.
Right? Like a pitcher throwing a fastball.
Perfect example.
Yeah.
So that ball's initial velocity has both a horizontal part and a vertical part. And we know the horizontal part stays constant.
Right, because there's no horizontal force acting on it.
Exactly.
But the vertical part is constantly changing because of gravity pulling it down.
Exactly. As the ball travels upwards, gravity is slowing it down vertically. And then as it starts falling back down, gravity's speeding it up vertically.
Okay.
And if you trace the path of that ball, you get that beautiful parabolic arc.
The math, like, perfectly describes what we see.
I know, it's amazing.
In the real world. It's incredible.
It is.
Are there any like special equations for projectile motion, like to describe those arcs?
There are.
Okay.
And they all stem from those same equations that we've been using for constant acceleration, just applied separately to those horizontal and vertical directions.
Okay. Wow, so many equations. Is there a way to kind of see how this all works in an example?
Absolutely.
Okay.
Let's go back to that cricket ball example you mentioned earlier.
Yeah, okay.
Let's say a cricket ball is thrown with an initial speed of 28 meters per second.
Okay.
At an angle of 30 degrees above the horizontal.
Okay, so we know its initial speed and the angle it's thrown at. What are we trying to figure out?
Let's try and calculate the maximum height the ball reaches.
Right.
To do that, we can use the equation for maximum height, which involves the initial vertical velocity and the acceleration due to gravity.
So first we need to figure out that initial vertical velocity. How do we do that?
We use a bit of trigonometry. The initial vertical velocity is just the initial speed, 28 meters per second.
Okay.
Multiplied by the sine of the launch angle, 30 degrees.
Hold on, let me grab my calculator. Okay, so sine of 30 is 0.5. So the initial vertical velocity is 14 meters per second.
Perfect. Now we can plug that value, along with the acceleration due to gravity, which is approximately 9.8 meters per second squared, into the equation for maximum height.
Okay.
And that gives us a maximum height of 10 meters.
10 meters, wow. That's pretty high.
It is. You wouldn't want to get hit by a cricket ball falling from that height.
Definitely not. And we could use similar equations to figure out, like, how long it takes to reach that height.
Exactly.
Or how far it travels before landing.
Exactly.
This is amazing. It's like we've unlocked the secret code.
I know. It's cool, isn't it?
Behind projectile motion, all thanks to vectors and some clever equations.
We started with those basic building blocks, scalars and vectors.
Yeah.
And now we're describing the motion of objects flying through the air.
I'm feeling like a physics whiz over here.
You are.
But I have a feeling there's still more to explore, right?
Oh, absolutely.
Like there's got to be other types of motion out there besides straight lines and parabolas.
You're right. While we've covered a lot of ground today, there's one more fascinating type of motion we need to dive into: uniform circular motion.
Uniform circular motion. Okay, that sounds intriguing.
It is.
But also a little intimidating. I think we all need a moment to, let all this sink in.
Yeah.
Before we tackle that one, we'll be back in a jiffy to uncover those mysteries of circular motion.
Stay tuned. Welcome back. I'm still, processing everything from last time.
Yeah.
Projectile motion.
It's a lot to take in.
It really is. But those equations predicting those perfect arcs, so cool.
It is, but get ready because we're going even deeper now.
Okay.
Into uniform circular motion.
Uniform circular motion. Okay. That sounds a little like a contradiction.
Right.
How can something be moving in a circle and, uniform at the same time?
So uniform here, it refers to the speed.
Okay.
So imagine an object, right? It's moving around a circle, but it's moving at a constant speed.
Okay. Like a Ferris wheel, maybe?
Exactly. Or a car going around a roundabout.
Okay, yeah, I can picture that. But if the speed's constant, isn't that, no acceleration?
That's where it gets tricky. Remember, acceleration, it's not just about changes in speed.
Right.
It's about changes in velocity.
Oh, right. Velocity is both speed and direction.
Okay, so even though the object's speed is constant, its direction is constantly changing as it goes around.
Right.
Which means it must be accelerating.
You got it. And this type of acceleration, it has a special name: centripetal acceleration.
Centripetal acceleration, okay.
Yeah.
I'm picturing it like there's a force pulling the object toward the center of the circle.
That's a great way to think about it. Centripetal acceleration always points towards the center of the circle.
Okay.
And it's what keeps the object moving along that circular path.
Okay, that makes sense. But then why doesn't it, spiral inward and crash if it's always being pulled towards the center?
Because the object's velocity is always tangent to the circle.
Okay.
Meaning it's always pointing in the direction it's moving at that moment.
So it's like a tug of war almost.
It
The
is
centripetal acceleration's pulling it in, but its own velocity wants to keep it going straight.
And those two things are perfectly balanced.
Okay.
Which is what results in that nice, smooth, circular motion.
It's like a dance, like a choreographed dance.
It is. This
is making me think about those, spinning amusement park rides.
Yeah.
You know, the ones that swing you around. The faster it spins or the further out you are, the stronger that pull feels.
That's right. And that feeling of being pushed outwards, that's actually your body's inertia.
Okay.
Its tendency to resist changes in motion.
Okay.
It's not actually a real force. It's just your body wanting to keep going straight.
Right.
While the ride's making you go in a circle.
Like when you're in a car that suddenly speeds up, you get pushed back in your seat.
Exactly. It all comes back to those laws of motion.
Well, this has been quite a deep dive.
It has.
Into the world of motion. Scalars, vectors, projectile motion, and now this uniform circular motion.
Yeah.
My brain is a little overloaded.
I bet.
But in a good way.
Good. It's been a pleasure sharing this journey with you.
Yeah.
It's amazing what we can learn about the world just from understanding how things move.
I know. I'm looking at the world a little differently now. Like seeing a ball flying through the air.
Yeah.
Or a car going around a track.
Right.
You know, you can almost see those invisible forces at play shaping how everything moves. It's pretty cool.
It's amazing.
When you think about it.
And this is just the beginning, really.
Yeah.
There's so much more to explore in physics.
Well, on that note, we've reached the end of our deep dive into the world of motion. We hope you enjoyed the journey as much as we did. Until next time, stay curious, keep those questions coming, and keep exploring the universe.